we present a new framework for the evaluation and mitigation of open vocabulary hallucinations in image captioning models. Image captioning is the fundamental task of describing an image with words. Although producing state-of-the-art results, vision language models, which are also known as VLMs, still suffer from hallucinations, spurious details that appear in the predicted captions. This behavior is demonstrated in the image below, as the model describes the appearance of the coffee drink as dimly shining and that there is a brown donut in its vicinity. We start with a short background on hallucinations in image captioning models. Traditional image captioning pipelines start by fine-tuning a pre-trained VLM on the desired dataset. Next, to further enhance the captioner's performance, it is optimized directly with respect to a NLP metric, like CIDR, for example, by a reinforcement learning algorithm. While the traditional pipeline improves the captioner, it does not directly optimize for hallucination reduction, and in some cases might even increase the hallucination rate. Therefore, additional hallucination mitigation techniques are applied, such as data augmentation methods, architectural changes, and advanced decoding and post-decoding methods. For a few years now, the most popular hallucination benchmark is CHAIR. For a given predicted caption, CHAIR parses out the objects and compares them to an annotated ground truth object list using exact matching. Any predicted object that is not included in the list is considered as a hallucination, and the final CHAIR score is the ratio between the hallucinated objects and all objects mentioned. Finally, CHAIR uses a synonym list. For example, when predicting dog instead of pug, beagle, or poodle, CHAIR would still include the predicted object as correct, as they are in the same object class. Despite CHAIR being very effective, its vocabulary is limited since it only considers 80 common object types. This is demonstrated in the center image, where it only evaluates the word scissors and ignores pencil, spool, thread, and mat. Furthermore, CHAIR cannot perform fine-grained distinctions between similar objects. For example, when compared by CHAIR, the prediction duck is not a hallucination with respect to the ground truth annotation goose, since both belong to the same object class, bird. Similar to CHAIR, many existing methods for hallucination mitigation ignore the open vocabulary nature of image captions, as they rely on closed vocabulary object lists. In this work, we propose a framework for addressing these hallucinations by leveraging recent progress in generative foundation models and RL optimization techniques. We start by proposing OpenCHAIR, an open vocabulary hallucination benchmark for image captioning. OpenCHAIR relies on two key observations. First, by replacing the closed object lists with a knowledgeable LLM, we are able to create a metric that can consider any predicted object. Additionally, this metric can compare objects with finer granularity. For example, the LLM knows the exact relations between tuna, salmon, and fish. It knows that tuna is a fish, and that tuna is not a salmon, and that fish might be a tuna or a salmon, depending on the context. Second, we can exploit the LLM's evaluation capacity by creating a new dataset with highly diverse objects. This is done by using state-of-the-art text-to-image models. We start with a ground truth image caption pair. First, the captioning model predicts a caption for the given image. Then, OpenCHAIR metric parses the objects out of the predicted caption. In this example, it parses bird and wall out of the caption "a bird stands near a wall." We then prompt a LLM to determine whether the parsed objects exist in a ground truth caption. Similar to CHAIR, OpenCHAIR returns the hallucination rate, the ratio of the hallucinated objects and total objects predicted. To create captions with highly diverse objects, we start by generating a large amount of synthetic captions. We do this by prompting a LLM to rephrase seed captions with objects taken from Coco. Next, we parse the objects in the captions and sample rare captions by filtering the ones that hold the most infrequent objects. Finally, we create the image caption pairs by prompting a diffusion model with a filtered caption. As a result, OpenCHAIR includes more than 2,400 different object classes, while the existing method CHAIR has 80, despite being similarly sized. In addition, thanks to the LLM's fine-grained evaluation, our metric highly correlates with human evaluations, improving the existing method. Finally, to show OpenCHAIR's diversity qualitatively, we display a small sample of OpenCHAIR objects. Image caption pairs with rare objects such as orchid, poncho, and honeycomb are seamlessly sampled by our automatic pipeline. Feel free to check OpenCHAIR on Huggingface using the QR code above. Now that we have an open vocabulary benchmark, we turn to propose MOCHa, an open vocabulary hallucination mitigation algorithm. As shown earlier, the second phase of the image captioning pipeline includes RL-based optimization. We propose an improvement to this block such that it will optimize for hallucinations as well. Following prior works, we adopt a RL environment where our agent is our VLM. At each step, the agent predicts a token, which is the action, and it is transitioned to a new state, which is represented by the image and the predicted token sequence until that time. The reward for each token prediction is 0, unless the agent predicts the end of sequence token. In this case, a NLP metric is applied to the whole predicted sequence, and the returned reward is the metric's outcome. Additionally, at this moment, the episode terminates. Lastly, the objective is to maximize the expected accumulated reward, and it is achieved by applying policy grading algorithms, such as reinforce. In our setting, we would like to give high rewards for good captions and low rewards for bad captions. We follow Wang et al. And define 3 properties for good captions: fidelity, or how consistent is the predicted caption with respect to the image; adequacy is the amount of details in the predicted caption; and fluency, the quality and clarity of the language in the predicted caption. To model fidelity, we use a natural language inference model, also known as NLI. In short, these models can predict the probability of a contradiction between 2 given sentences. The fidelity reward will be 1 minus the contradiction probability between the prediction and the ground truth caption. To model adequacy, or detailedness, we use BERT score. BERT score computes a similarity score between the contextual embeddings of the predicted and ground truth captions, which correlates to the amount of detail that overlaps between the two. As for fluency, we follow prior work and add a KL regularization term to our reward. This is because we do not want to deviate too much from the supervised fine-tuned model, as it already has great linguistic knowledge, and in addition, this term restrains the model from converging to adversarial solutions that hack the reward model. We combine the 3 and result with our final reward term, where the parameters alpha and beta are controlled by the user. Our RL algorithm iteratively collects a batch of data from the image captioning model M, which can be seen on the left side, and evaluates it. It then applies an optimization step, which can be seen on the right side. This process is repeated iteratively until convergence. Results. We show captions predicted by Blip Large before and after MOCHa fine-tuning. One prominent effect of MOCHa tuning is that it adapts the predicted captions to the model's existing knowledge. This is evident in the example in the middle. The baseline model predicts a stop sign that says, "You gave the reason." The model does not understand that the word stop is also a part of the sentence and also makes mistakes when reading the handwritten message, which says, "You can't stop the Red Sox." On the other hand, the MOCHa-tuned model only mentions the handwritten message, but does not attempt to read it out. MOCHa also improves other hallucination types, as can be seen in the examples on the left and right. Furthermore, our visual tool shows additional 1,000 randomly selected examples of MOCHa-tuned captions. Additionally, we show that for a variety of model sizes and architectures, MOCHa tuning reduces hallucinations while maintaining the same level of detail. The graph on the left shows fidelity metrics. Each bar group is a different model, such as Blip2 or GitBase, and the colors represent the improvement in each metric score. The graph on the right shows the adequacy metrics and uses similar notations. Lastly, feel free to check our paper for additional analyses and experiments. For example, we empirically show an inherent trade-off between our reward terms and how we let the user control it with a single parameter alpha. Our work does have a few limitations. First, MOCHa's reward model compares the predicted caption with textual ground truth captions, which might not include all information contained in the image. Second, our LLM evaluator in OpenCHAIR cannot see the image. Similarly, it relies on a textual caption that might not convey all the image's content. To conclude, state-of-the-art image captioning models suffer from hallucinations. In addition, the vast majority of existing hallucination metrics and algorithms restrict themselves to the limited closed vocabulary setting. We propose OpenCHAIR, a highly diverse open vocabulary hallucination benchmark for image captioning models. OpenCHAIR leverages LLM knowledge in order to replace CHAIR's closed vocabulary object lists. Furthermore, we propose MOCHa, a deep RL framework for state-of-the-art open vocabulary hallucination mitigation. MOCHa boosts performance for a variety of model sizes and architectures.